Okay, so a transverse wave, if I pull this back and then let go of it, see how that energy goes parallel with the spring. So you see this pulled back, it goes down, and it comes back. So what you hear as sound is a whole series of those with nitrogen and oxygen molecules being compressed and expanding. That's what you hear as sound. Now, on a transverse wave, that's going to be something like this, okay? Where the energy is, the wave is going back and forth like this, but the energy of the wave is going this way. So there's going to be three main things that we're going to talk about when you talk about any type of wave. How fast it's going, the wavelength, and the frequency. So I'm going to establish what we call a standing wave. So this is, no, so just hold that. Okay, so let me get that going like this. Okay, so this is as simple as it gets right now. Is what we call a standing wave. So that's one wavelength. So imagine that you could freeze that in place. So it's starting down there at Davmai. It goes up, it goes through the middle, and then it ends up back here. So let's say that distance between Davmai and me is 3 meters. So if I have this like that, okay, that wavelength would be 3 meters. Now, if I do something simple like this, okay, now, if you think about it, that wavelength from here to there, that's half of the wavelength. So it would actually start there, come out like this, it would stop here, and then you'd visualize that the other half going back out this way. So like this, that's a half a wavelength. But if I have that, that's an entire wavelength, okay? Now, if I go even faster, like that, okay? Now, I've got a lot of wavelengths in there. But here's the interesting thing. Okay. Popcorn, I need you to count, okay? So, I need you to count. Olivia, I need you to count out loud to 10. While she's counting out loud to 10, I need you, Popcorn, to count how many times that goes towards you, okay? So she's going to count to 10. You're going to count how many times. So like, I'm going to get it going. Like that would be 1, 2, 3. All right? Yeah. Got an idea what you're going to count? Yeah. You're going to count to 10. You're going to be our timer. Okay? All right. You ready? Okay. Whenever you want to start, you guys make it happen.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
How many did you count?
18.
18. Okay. So she counted 10. That was like 18. So knowing that that was 10 seconds and you counted 18, what could we figure out? Frequency, which would be what? 10 over 18 or 18 over 10?
18 over 10.
18 over 10. Why?
Because
It's an event per unit of time. So we can take 18 and divide it by 10 to get 1.8. Okay, so that had a frequency of 1.8, right? Now, that distance right there, that's like half the wavelength. So if the distance between us right now with this wave, if that's 3 meters, the entire wavelength would be 6 meters, okay? Now we're going to do this again. You got to count to 10. You got to count your waves, okay? So now we're going to do this, okay? All right? Now, what's the wavelength? 3 meters. Because now I have an entire standing wave within this. Hold on, let me get it going. You have to hit it just right. Okay, there we go. All right, Olivia.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
Okay, what'd you get?
35.
Okay, about 36, right? About twice as much. So, as the wavelength got shorter, because we went from 6 meters to 3 meters, wavelength got shorter.
Frequency goes up.
Oh, frequency goes up. Okay? Now, what would happen to the period of the oscillation? It goes down because frequency and period are inverses of each other, right? Okay. Now, we're going to do this again. Okay? Ready? You're just going to take some intense counting. Okay? I got faith in you. Okay. All right, Olivia, let's just do 5. Just count to 5.
Okay. 1, 2, 3, 4, 5.
Okay.
22.
22, right? What happened to the frequency?
Went up.
Oh.
Okay? Well, it would have basically gone to like 44 because she only counted to 5. So if it went to 10, it had gone all the way to like 44. So here's what I want you to get out of this. As the frequency becomes bigger, what happens to the wavelength? That becomes smaller. It's an inverse relationship between the two of them. Now, the last thing we're going to talk about is energy. Okay? I'm creating the energy to make this happen. So this is what I want you to observe. Okay, so we got one more. Have mine. Okay, so if I do this, does that take much energy from me?
No.
No. This is as simple as it gets, like back and forth and back and forth. Okay? That's a really, really long wavelength at a low frequency. Now, if I do this, okay, like that, what happens to the amount of energy that I have to put into it? A lot more. So, but what happened to the frequency? So, is there a direct or inverse relationship between energy and frequency? Direct. So, the higher the frequency, the more energy that takes. Okay. Thanks, Gavin. Well done. That was a lot.
I'm scared to plug it back in.
Oh, you're fine.
We did not have to make that. That is not over. Do not have to make that coordination.
Hold on. There's like count. Oh, we gotta lose count. Because when she starts counting, then always have to think about that.
Well versed.
Who's that? Wait, did he go over? Yeah, this is this. It's not related.
Oh my gosh, I've seen this place before. Yeah, but it's like Yuga.
What's on the scene?
It looks like
Is it like this?
Remember, because it was like color.
Okay. So the speed of any wave, whether it's light, sound, doesn't make any difference. The waves, like in that spring, doesn't make any difference. Any velocity of any wave, and this, like I said, that V doesn't have anything to be specific. This is just a general way of expressing it. So this is the velocity that it's going to travel through. Is wavelength times frequency. So this is the Greek letter lambda. It's like a walking, it almost looks like a praying mantis. Okay? Which is the Greek letter lambda. That's wavelength. That's going to be in meters. Then you have frequency. Frequency is generally expressed in one of three things. It's either 1 over seconds, s to the minus 1, or typically it's just referred to as hertz. Okay? Hertz all means the same thing. Now, that's one way to express this. Sometimes you'll see it written as velocity equaling lambda, and that's the Greek letter nu, okay? Which is kind of like the letter V, but it's like a wind-blowing V. So this is the Greek letter nu. So they kind of gone away from this just because people were getting confused because you see V over here, and then they think that's also V, even though it's the Greek letter nu. So the physics purist will have it written as V equaling lambda nu. But you also see it written as lambda frequency. Now, if you're talking about the speed of sound, and the speed of sound changes depending upon atmospheric conditions, most notably temperature and humidity. But generally, we're going to use the speed of sound to be 343 meters per second. So this tuning fork, right? So that vibrates at 880 hertz. So if I know the speed of sound in the room is 343 meters per second, and I know that this is vibrating at 880 hertz, what can I find? I can find the wavelength, okay? So if I know my frequency is 880 hertz, okay? How am I going to get lambda? Yeah, and if you look at what happens with the magic of the units, you're taking 343 meters per second, divide that by 880, which is 1 over seconds, which is the same as multiplying by the seconds cancel out, and you get meters. Okay? So, somebody take, for the sake of argument, popcorn, take 343 and divide it by 880. 0.39 meters. Okay? And that's a decent length, okay? That's like here, okay? That's like 0.4 meters. Now, here's the dichotomy of how we represent sound. So that 0.39 meters is technically the distance between like a compression, and then you would have like a rarefaction where they're far apart, and then you'd have like another compression. So that 0.39 meters would be the distance between either like the 2 points of maximum compression or the 2 points of the low side on the rarefaction. But that's tough to draw, okay? And it's tough to represent visually. So even though sound is very much the kind of quintessential longitudinal wave, a lot of times when we talk about sound, we'll still draw it as a transverse wave and go, oh, this is the wavelength, that's 0.39 meters. That isn't how sound actually works. Sound doesn't actually travel as a longitudinal wave, but visually it makes it easier to represent and show, oh, this is the wavelength, okay? So this is the misleading part about sound and how we represent it. We draw it as a transverse wave because that's easier to draw than a couple of dots close together with each other, okay? So it's not a transverse wave, but we draw it as a transverse wave. Now,
Is it longitudinal?
huh?
Is it longitudinal?
It is longitudinal, but we draw it as a transverse, okay? But that's the thing, we draw it that way, but that isn't actually what happens. Okay, so another way that you can see how frequency affects this is, let's go to the back of the room, unplug the camera. Actually, just shut off the camera and we'll start it back up in the back room.